Okay, so welcome to class. Today we're going to be starting a new chapter, chapter 14 in your TRO book, called Chemical Equilibria. All right, and this is going to be a pretty important topic in Gen Chem 2. As you're going to see, we're going to start talking about equilibrium today, and then keep talking about it for 3.5 or so chapters. So it's a pretty important topic. We're going to start with the basics today, and kind of get a grasp on this, and then we'll work our way up, like I said, through the next few chapters. Right? So the topic is chemical equilibria, and you guys know by now, right? I always like to start with what we know, right? And kind of build up from there. So we've talked about equilibrium already, both in this class, and if you think about it, even going back to your Gen Chem 1 days, right? In fact, when you first learned about acid-base chemistry, right? You learned about 2 different types of acids, right? You classify them as either what? Strong or weak, right? So somebody give me your favorite strong acid. Or hydrochloric, it's like the one they always use, right? So you guys know, right? What happens to hydrochloric acid, right? When it's in solution, if you write a formula for this, right? You write a reaction for this. HCl aqueous looks like what in solution? It really doesn't look like these HCl molecules stuck together. It looks like what, JC?
H plus and Cl minus.
Yeah, the fancy, the D word, it dissociates 100% of the way. You guys know that because it's a strong acid, strong electrolyte, all that good Gen Chem 1 stuff. In a very simple picture to H plus Cl minus. We'll study Bronsted-Lowry acid-base chemistry later, and we'll learn more of the story. But for now, right, that's the main idea, is that it dissociates 100%. Something very different happens, as you might recall, with a weak acid. So for example, if you look at the weak acid as this formula, right, this acid is called what? Acetic acid. You all remember that from Gen Chem 1, right? When acetic acid goes into solution, when it dissociates, it does not go 100% of the way. You've got to remember that, right? It's weak electrolyte. And so how did you depict that? Even back in Gen Chem 1, you maybe wrote it this way when you wrote the reaction. Do you remember what was different about the reaction? How you wrote it here versus here for acetic acid? What was that?
Was it the arrows?
Yeah, the 2 arrows, right? Not the double-headed arrow, right? That's for resonance. Remember that whole delocalization thing, right? But with the 2 arrows, you usually draw it like this, right? Showing acetic acid reacting with water, right? And you draw the 2 arrows, which represent an equilibrium scenario. Right? We say that the acetic acid and water, when they react, are in equilibrium with the base of acetic acid, like the conjugate base, which is called what? Acetate, that anion, when that proton is transferred, right? When the acid-base chemistry occurs, you have a negative charge, right? And then you would get what when the H goes from here to here? You get the hydronium ion. So you guys remember a little bit of this even from your Gen Chem 1 days. And like I said, we're going to come back to that type of scenario much more detail in a couple of chapters when we start applying equilibrium to acid-base chemistry. Right? Get a little bit more quantitative with it. Right? For now, at least you've seen this before, right? All right. So you guys know I'm a big believer in, you got to think of what's going on in the flask, right? I know there's a lot of number crunching. It's Gen Chem, so there's a lot of calculations. But if we can't relate it to sort of the concept, the idea of what's going on at that molecular level in the beaker, we're going to be in trouble, right? That's a lot of what we need to do in this class. So in terms of what's actually happening and what's represented by those 2 arrows, right? Let's think about that. So somebody tell me, right? When you say this is an equilibrium, what does that mean to you, right? What does that mean, Haley? It has something to do with equal. Let's start there, right? What do you think, Courtney? Perfect. It's dynamic, and that's the key. When we apply equilibrium to chemistry, we have to remember we're talking about dynamic equilibrium, and that's a very important term. Glad you said that. Dynamic equilibrium. In other words, you guys know this by now, right? In chemistry and in life, right? Nothing is ever static, right? We get into this trap sometimes. We draw Lewis structures with electrons, and we say they sit on this atom or they're between these atoms. But when we learn about, delocalization, we know everything's in flux. Same with equilibrium. Everything's in flux, right? So when we talk about this equilibrium expression, what we're saying is the reaction's actually happening in both directions simultaneously. Right? In other words, you get a little bit of the forward direction while you're getting a little bit of the reverse direction. Right? But if you could take a snapshot, right, of this scenario, you would find that one of the sides, either the left or right, reactants or products, is favored. In other words, there's a greater net concentration at any given time of maybe products versus reactants, or vice versa. Actually, in this case, does anybody know which? Right? Which has the greater net amount or concentration of species? Is it the left or the right? Would we say this is a reactant-favored or product-favored reaction? And how would we know for sure? Anybody know? Take a guess. If this is a weak acid, so why was this strong again? Because it goes 100% of the way, right? So then why is this weak? Well, it doesn't, right? And most of these weak situations, it's the reactant side of the equation that's favored, right? And you know this is Gen Chem, especially Gen Chem 2, which means we have to quantify that, right? And we quantify that by writing what's called an equilibrium constant, right? Or an equilibrium expression to describe this reaction. So the equilibrium constant for this reaction would be written as a ratio. And if you get nothing else from this lecture, this is the most important thing to take home about equilibrium constants. All they represent are ratios, relative amounts of products to reactants. And in fact, the form of an equilibrium constant, the way you write it, is as a ratio. It's given the symbol big K, and we write it as a ratio of the concentrations of our products divided by the concentrations of the reactants, with a few caveats that we'll talk about. Okay. In this case, we would write the big K as the acetate anion multiplied by the hydronium cation, right? Plugging in, remember what the brackets mean from last time? That's what molar concentrations is what we're using in this course, okay? A little bit more to that, but we'll talk about that down the road. For now, we're just considering molar concentrations, just like you've always done, of products over reactants, with one disclaimer, right? Those of you who, you all know I like to tell you, you got to read ahead. If I know I asked you to read ahead into the rules, basic rules of writing these, what was one of the rules that we have for writing equilibrium constants with regard to how pure liquids or pure solids affect the expression? You remember that, JC? Did you read that yet?
Yeah, liquids and solids, you don't put them in the equation.
They don't appear. Why is that? There I go meddling again. Right? So what do I always ask this. What was that, Derek?
Because they're represented by a 1.
When we talk about activities, and when we go a little bit deeper, that's correct. For our purposes, we say, well, solids and liquids, their concentrations don't change appreciably. Like, say, something in solution. We know these concentrations vary if it's an aqueous solution. Or a gas concentration is very sensitive. It's compressible, very sensitive to changes in concentration. So for gases, things in solution, we include those. For pure solids and liquids, we don't. In other words, the water concentration relative to everything else isn't changing, H2O by itself. So we get this expression for big K. And then we can use that in subsequent calculations. Okay?